Welcome back, everyone. Ready for another deep dive? This time, we're diving headfirst into the fascinating world of computer networks.
We've had so many requests to tackle this one, and we aim to please.
And we're going straight to the source, Behrouz Forouzan's Data Communications and Networking.
A true classic. Dense, I'll admit, but packed with essential knowledge.
A real brick, right. But don't worry, we're here to unearth that knowledge gold for you, piece by piece.
Exactly. We'll guide you through the jargon and make sure you come up for air with a clear understanding.
So before we get lost in the technical weeds, let's start with something we can all relate to. Ever sent a picture to a friend across the country? Or how about video chatting with family overseas?
Pure magic, right?
It really is, but that magic is all thanks to data communication.
It's mind-blowing how we take it for granted sending massive amounts of data across the globe in the blink of an eye.
Absolutely, but how do they do it? How do computers, actually talk to each other? It's not like they speak our language.
It's all about signals. Think of it like their own secret code. Computers translate our words, pictures, videos, everything into signals that they can transmit.
So instead of English or Spanish, it's
No.
all ones and zeros, right? Like those digital clocks.
You got it. It all boils down to two types of signals, analog and digital.
Okay, so analog, that's like what? Old school radio waves?
Exactly. Continuous waves like ripples in a pond. Forouzan gives a great explanation of this in Chapter 3.
And digital is more like those on-off switches.
Precisely. Discrete values like steps on a staircase. Forouzan talks about this all the way back on, page 3 of Chapter 1, Data Representation.
Right, so how do those signals actually travel? Through the internet tubes.
You're not far off. It's not magic, though. They use various media like cables, fiber optics, even radio waves.
So it's kind of like choosing the right tool for the job.
Precisely. And sometimes they even need a translator, like in the good old days of dial-up internet. Remember those ear-splitting modem noises?
Oh, how could I forget? The soundtrack of the early internet.
Those modems played a crucial role. Forouzan explains it nicely on page 82 of Chapter 3. They converted digital signals from our computers into analog signals that could travel over telephone lines.
So those screeching sounds were actually data. Wild. But it's more than just sending signals willy-nilly, right? We need some organization, a system to manage all that data traffic.
Yeah, absolutely. That's where networking comes in, creating a system of interconnected pathways for our data to travel.
Like building roads and highways for our digital information.
A perfect analogy. And just like with any transportation system, we need rules, regulations, and a well-defined structure to prevent chaos.
Okay, so we've got our data all packed up, ready to hit the digital highway. But what kind of highway are we talking about here? Are we thinking like a massive freeway, a network of back roads?
That's where network topologies come in. They're like the blueprints for our data highways.
Blueprints, I like it. So what kind of blueprints are we working with?
Well, you've got your mesh networks, where every device is connected to every other device. Forouzan talks about this in Chapter 1.
So it's like super interconnected, everything's linked up.
Exactly. Very resilient. If one connection goes down, the data can just take a detour.
Smart. What else?
Then you've got the star topology, where all devices are connected to a central hub.
So like a central command center directing traffic?
Right. Simpler setup than the mesh, but if that hub goes down, you're in trouble.
Makes sense. Anything else?
The last one we'll touch on is the bus topology, where all devices share a single communication line. Forouzan describes these on pages 17 to 19 of Chapter 1 if you want to take a closer look at the diagrams.
A single line. Isn't that like a bit of a bottleneck?
It can be, yeah, if there's a lot of traffic. But each topology has its own strengths and weaknesses depending on what you need it for.
Okay, that makes sense. But no matter what our data highway looks like, we need some serious traffic rules to manage all that data zooming around, right?
Absolutely. We can't have data collisions. That's where network models come in. They lay down the law, so to speak.
So like the digital equivalent of the highway patrol.
You got it. First thing introduces two big ones, the OSI model and the Internet model. You can find that in Chapter 2, page 21.
Two whole models. Why do we need two? Is one like the backup?
Think of it this way. The OSI model is like the ideal blueprint with 7 perfectly defined layers of communication. Beautiful, elegant, but...
But not always practical in the real world.
Exactly. The Internet model is the one we actually use. It's a little more rough around the edges, but it gets the job done.
So more like the streets of Rome than a little chaotic, but full of history.
I like that analogy.
So how does this internet model work? Can you break it down for me?
Sure. Imagine you're sending a postcard. The application layer, that's where you write your message. It's the layer where our apps, live, email, browsers, all that good stuff.
Makes sense. What's next?
Then you've got the transport layer. That's like putting your postcard in an envelope, writing the address, and picking the right postage.
So it's all about making sure the data gets to the right place.
Exactly. Reliability and all that. Then comes the network layer. This one's like the postal service itself, sorting your postcard and figuring out the best route to deliver it.
Like a digital mailroom. Forouzan talks about network addresses on pages 47 and 48 of Chapter 2, right?
You got it. It's how devices on the network find each other, like using a postal code.
So much happening behind the scenes, and I never even realized it.
It's pretty incredible. And the final layer, the link layer, is like the mail carrier actually physically delivering your postcard. It deals with the nitty-gritty details of how data gets transmitted over the physical medium.
So we're talking cables, Wi-Fi signals, that kind of thing.
Exactly. It's the layer that connects our data to the physical world.
Wow. Okay, so we've gone from blueprints to mailrooms. This is way more interesting than I ever thought networking could be.
It's a whole world of its own, and we're only just scratching the surface.
Speaking of scratching the surface, we talked about those physical mediums earlier, and I have to admit, I'm picturing those old telephone cables, you know, the ones you could trip over.
Ah, the good old days. Forouzan talks about those twisted pair cables in Chapter 7. Reliable, but not exactly built for speed.
So what are we using now? What's replaced those tangled messes?
Fiber optics, baby. Think beams of light carrying data at lightning speed.
Now that's what I'm talking about, the data autobahn. So are we talking like Star Trek levels of speed here?
It's getting there. Forouzan describes fiber optics on those same pages, actually 193 to 202 of Chapter 7, if you're curious.
I might just have to check that out later. But even with those light speed connections, there's got to be a limit, right?
There is. It's all about bandwidth. The wider the road, the more data you can send at once.
Makes sense. So how do we get those wider roads?
Well, we've got a few tricks up our sleeves. One of them is called multiplexing.
Multiplexing sounds impressive. And probably complicated.
Not at all. Forouzan explains it pretty clearly on page 169 of Chapter 6. Imagine a highway lane dedicated to carpools.
Okay, I'm picturing it, more people and fewer cars.
Exactly. Multiplexing is like that, squeezing more data through the same bandwidth.
Clever. I like it. So we're basically getting more bang for our buck, bandwidth-wise. But even with all this amazing tech, we're still limited by the laws of physics, right?
Afraid so. Even our data superhighway has a speed limit. It comes down to something called the Nyquist and Shannon theorems.
Those names sound familiar. Weren't those mentioned way back in Chapter 3?
You've got a good memory. Pages 86 and 89, if you want to look them up. Essentially, the maximum data rate depends on the bandwidth and something called the signal-to-noise ratio.
Signal-to-noise ratio. Is that like when you're listening to the radio and it gets all staticky?
Precisely. Noise is anything that interferes with the signal, and too much noise means lost data.
So it's like trying to have a conversation at a rock concert. Hard to hear anything over all that noise.
Exactly. The clearer the signal, the better the communication. But even with a perfectly clear signal, we can still run into problems.
Like what? Don't tell me traffic jams on the data highway.
Worse, errors. Sometimes those data packets get lost or corrupted along the way, and we need a way to detect and fix those errors.
So we need like a data mechanic to make sure those packets are in tip-top shape.
Exactly. And Forouzan has got us covered. He dives deep into error detection and correction in Chapter 10. But maybe we should save that for next time. We've covered a lot of ground already.
Okay, so we've sent all this data on its way down the data superhighway. But how does it know where to go? It's not like our data packets have little maps, do they?
That's where the magic of routing comes in. We have these things called routers. They're like the GPS guides for our data packets, making sure they reach the right destination.
So they're constantly analyzing traffic, finding the most efficient routes, preventing any digital pileups.
That's exactly it. And they have to consider all sorts of factors: bandwidth availability, congestion on different routes. Forouzan actually talks about this in Chapter 22, page 651, if you want to check it out later.
I'm starting to think these routers deserve a vacation with all that work. But it's amazing how they make those routing decisions so quickly.
It really is.
Yeah.
And just like we have different levels of postal service for different needs express, priority, you name it, we have different protocols for sending data.
Ah, yes, like TCP and UDP. We touched on those briefly before, but Forouzan really dives deep into them in Chapter 23, right?
You got it. Page 703, I think.
Yeah.
TCP, or Transmission Control Protocol, if you want to get it technical, is like sending a package with insurance and tracking.
So it's the worry-free option for our data.
Exactly. It guarantees that all the data arrives in the right order, without any errors.
Like a digital guarantee of delivery. And then what is the other one? UDP.
Yep. User datagram protocol. It's more like sending a postcard faster and more efficient, but no guarantee of delivery.
So you might use that for, say, streaming a live video, where a few dropped packets here and there won't really be noticeable.
Exactly. Sometimes speed trumps perfect accuracy.
Makes sense. It's all about choosing the right tool for the job. But you mentioned earlier something about digital signals being like stairs, and that there are different ways to build those stairs.
Ah, you're talking about line coding. It's like choosing the right building materials for our data staircase, making sure it's sturdy and won't collapse under pressure.
So different coding schemes for different scenarios.
Precisely. And Forouzan delves into this in Chapter 4, around page 108. He gives the example of Manchester encoding. It's a way of making sure the receiver can clearly distinguish between the steps of our digital signal, preventing any missteps.
Clever. It's all about clear communication, even at the signal level. Speaking of clear communication, we also briefly touched on sampling and the Nyquist theorem earlier. And I have to admit, that one kind of went over my head.
No worries, it's a bit of a brain twister. Imagine trying to describe a movie to someone but only telling them about every other scene. They miss a lot of crucial information, right?
That's one way to ruin the ending.
Right. Well, it's the same with digital signals. We sample analog information at certain intervals, creating those digital steps we talked about. And the Nyquist theorem, which Forouzan explains around page 122 of Chapter 4, tells us that we need to sample at least twice as fast as the highest frequency in the signal.
Otherwise, we end up with a blurry, incomplete picture like that poorly described movie.
Exactly. And Forouzan uses a really interesting example to illustrate this, the hands on a clock.
Okay, now you have my full attention. Clock hands and data signals. How does that even work?
Picture this. You're looking at a clock, but only for a split second, several times a minute. Depending on how often you look and the speed of the hand, you might think it's moving forward when it's actually moving backward.
Whoa, mind blown. I see what you mean.
It's all about perspective and having enough data points to accurately interpret what we're seeing.
That's a powerful analogy. And a great way to wrap up our deep dive into the world of data communication. From analog waves to digital highways, error detection to clock hand analogies, we've covered so much ground.
It's a testament to human ingenuity, really, how we've managed to create these invisible pathways for information to travel at lightning speed. It's truly remarkable.
All those cat pictures and video calls, they suddenly seem even more magical now. And on that note, we've reached the end of our data journey. But remember, the learning never stops. If you're feeling adventurous, why not grab a copy of Forouzan's book and explore the fascinating world of data communication further? Until next time, happy diving.